It is showing host disabled participate screen
Okay,
share.
okay. Let me give you permission. The permission has been given to you. You can run now.
Yes. Yeah, is it visible?
So let me introduce you. What?
Hello.
Hello. Yes, your skin is now visible completely.
Oh, okay. Okay.
So let me introduce you first formally. So Pallabi Chaterjee is a research scholar in IIT Tirupati, working with Dr. Ranjan Krishna Modak, and her area of research is theoretical condensed matter physics. And today's title of her talk is One-Dimensional Quasicrystal. So I am I am handing over to you, Pallavi. Please, you can start now.
Yeah, first of all, I would like to thank the organizer for giving me the opportunity to present our work here. So today I will present our work, one-dimensional Lebesgue quasicrystal. So at first I will give some background, some work which are already in the literature. Then I will talk about the notion of fractional quantum mechanics. Then I will tell about the motivation why we use this fractional quantum mechanics. And then I will tell how one can generate Lebesgue quasicrystal using this fractional quantum mechanics. Then I will show some of our results. Then I will conclude stating some future plans. So at first, what is Anderson localization? So if a system is having a strong enough disorder, so in presence of strong disorder, all the single particle state of the system will be localized, and it is irrespective of the dimension if the strength of the disorder is strong enough. So if it is happening, then the system will not show any transportation property. The diffusion will be zero of the system, and the system is called Anderson insulator. But one can show that in 1D and 2D, if the disorder strength is small also, then also one can get the single particle eigenstates as localized. And in 3D, in presence of a teeny amount of disorder, the delocalized states are also present. To see the localization, we have to give a very strong disorder in 3D. So now here is one simple example of Anderson localization in 1D. So this is the Cj dagger is the creational operator and Cj plus 1 is the annihilation operator. It is representing the hopping of the electron from one side to another side, and it is nearest neighbor hopping. So here is a Hermitian conjugate of this term. So without this red term, if we plot the mod psi square, the probability amplitude, one can see that the wave function will be distributed to all over the sides. So one can say the wave function is delocalized. Now, if we add this red term, which is containing this nj, that is the number operator, and if we write the Hamiltonian in a matrix form, this Cj dagger Cj will create the diagonal entries of the matrix, and this epsilon j is a random number which we can choose between these windows minus w/2 to w/2. And if we choose this epsilon j randomly from these windows, then all the diagonal entries will be random. And in presence of this random disorder, here I took w equals to 5. So here we give a finite amount of disorder. So one can see the wave function mod psi square is localized to a particular site. So in absence of disorder, that means W equals to 0, that is epsilon j equals to 0. In that case, all the single particle states are delocalized. And in 1D and 2D, if we give a teeny amount of disorder also, then the particle will be, the single particle states will be localized to a particular sites, and the localization form will be exponential. The wave function will be exponentially localized. Suppose it is localized to R alpha sites, then it will be localized exponentially like this, where this zeta is the localization length. Now, how one can characterize this localization or delocalization, whether the state is localized and delocalized? To do that, we can use, there are many tools to investigate this localization, delocalization. One of them is to investigate the inverse participation ratio. So which is given by this expression. Here we are, this k is the number of states. So for k state, we are k number of state, we are writing the IPR value like this, and we are taking the sum over all of the sites. So now for delocalized states, as the wave function is distributed to all of the sites almost equally, so if we calculate mod psi to the mod psi square, then probability will be 1 by n. And if we take the fourth power, it will be 1 by n square. Now, if we sum over all the sides 1 to n, then n by n square, it will be 1 by n. So here is a system size dependency for delocalized states. So it is scaling with system size, IPR value. Now for a localized states, as the particle is localized to a particular site, the psi whole to the power psi I k square will be 1, almost equals to 1 for the site which where the particle is localized. So if we take the fourth power, it is also will be almost equals to 1. And for the other side, it will be very much small. So here, and for extreme localized states, the IPR value will be approaching to 1. So for localized states, there is no system size dependency. And for delocalized states, there is a system size dependency. Now, in 1D and 2D, for the Anderson case, we didn't see any localization to delocalization transition, because in presence of a teeny disorder, all the states are localized here. So in 1D, if we want to see the localization, delocalization transition, one can use a different kind of model, which is called Aubry-Andr model. Here, the kinetic part of the Hamiltonian is same, but here we are using a different kind of disorder. Actually, this is not disorder. Here we are using a potential like this, but this is having this is a periodic potential, and but the period of the potential is say 1 by beta, and if the lattice period is a, then this ratio of these two periods, the periods of this potential and the lattice potential, has to be a irrational number, which guaranteed by taking beta as a irrational number, √5 minus 1 by 2. So though it is a periodic function, the electron will see this potential as randomly distributed because of this irrational beta value. And phi, we are choosing between this 0 to 2 pi window, any random number. So in presence of this kind of potential, one can see a clear delocalization to localization transition, where in the delocalized states, the IPR value here, it is scaling with system size. And for localized states, the IPR value is approaching to 1. So now, another feature is mobility edge. So what is mobility edge? If the IPR value is energy dependent, then we can say the system is having a mobility edge. And some models which are having the beyond nearest neighbor hopping amplitude, those models with incommensurate potential are showing this mobility edge. And some of these models are Gaussian hopping model, exponential hopping model, power law hopping model, etc. So now here one property, if a model is having a property, the self-duality, what is that? If the wave function, if we do some transformation, under the transformation, we are going to a dual space, and the in real space and the in dual space, the wave functions are satisfying same eigenvalue equation. But if it is localized in a dual space, it will be delocalized in the real space, and vice versa. So if we consider this self-duality condition, then one can, from that, one can get one can assume or one can predict there is a delocalization localization transition, and that transition point or the mobility edge point can be calculated using this self-duality condition. So here is a one model which shows this mobility edge, where one can see this model is not nearest neighbor model. This Cj dagger Cj plus n, and this hopping amplitude is given by t into exponent. It is exponentially decaying. So if we do some transformation here in dual space, we can see that this H and this will not be same as the real Hamiltonian. So in dual space, this H and this hopping amplitude will change. But if we want to get back our same Hamiltonian, we have to give some condition on H. And here the condition is cos hyperbolic P equals to E plus T by H. And we know that if it is localized in real space, it will be delocalized in dual space. So one can assume that if this condition is satisfying, there is a transition from delocalized to localized states. So here is a, sorry. So here is a energy spectrum of this Hamiltonian, which is having a delocalized states. This blue is representing the delocalized states, and the pink is representing the localized states. And here the mobility H line is representing by the solid straight line, which separating the delocalized and localized states. And here the mobility H is a straight line representing by this cos hyperbolic P equals to E plus T by H, which is energy dependent. Now I will talk about fractional quantum mechanics. So in normal quantum mechanics, when we are calculating the probability of a particle for going from one position to another position, we are using the Feynman path integral approach, and we are integrating over all possible paths, where we are taking those paths at Brownian trajectories. But if we replace those Brownian trajectories with Levy flights, which is having this kind of probability distribution 1 by mod x to the power alpha plus 1, then if we follow the same path integral approach, then the Schrodinger equation we will be getting will be a fractional kind of Schrodinger equation, which is having this E proportional to k to the power alpha kind of dispersion relation. If alpha equals to 2, we will be getting back our normal quantum mechanics and normal dispersion relation E proportional to k square. So now this is the fractional Schrodinger equation, where P alpha is the alpha power of the momentum operator, which containing the d alpha mod x. This is the reached fractional derivative, which is having the alpha order derivative term. So if alpha equals to 2, it will be having second order derivative term, and this will be h cut square, and this d alpha will be 1 by 2m for alpha equals to 2, and we will be getting back our normal Schrodinger equation. And this is the general form of the Schrodinger equation in space fractional form. And now, why we are using this space fractional quantum mechanics? There are some examples, some applications of Levy flights. This motion of a particle in a rotating flow, traveling behavior of humans. This the path they are following in these processes are Levy flights path. And recently there are some experimental proposals of verifying space fractional quantum mechanics. So that's why we are studying this thing. So here one optical realization of space fractional quantum mechanics. So they studied the evolution of light beams governed by the fractional Schrodinger equation, which is given by this equation. And this light beam is going through a quasiperiodic type of potential, which is given by this. And they have studied the IPR the dependency of IPR, and for different alpha value. This chi is the continuum version of IPR, and they have showed some localization to delocalization transition is happening if we consider this fractional quantum mechanics. And but they studied only this complete delocalized and complete localized states. In between there are some also phases are there, those mobility edge phases that they didn't mention in this paper. So now how one can generate this quasi-periodic type of potential in experiments. So if we take one lattice which is having a periodicity of cos omega 1x, and another lattice which is having the periodicity cos omega 2x, and where this omega 1 and omega 2, these two ratio is incommensurate, then we can represent that ratio by a rational number. And if we superimpose these two lattice, then we'll be getting a quasi-periodic kind of lattice. So now they have studied the continuum version, but we discretized the space-fractional Schrodinger equation, and we got a lattice version of the space-fractional Schrodinger equation, and which is given by this Hamiltonian. Now, usually this space-fractional Schrodinger equation, people are starting in the range 1 to 2, but as we are discretizing here, we extended the range to 0 to 2 because the discretization version is not having any problem with this range. And this is the hopping amplitude of our model, which is given by these three expression in this three region. So now if this is our model and in presence of that incommensurate potential. Now if we plot this hopping amplitude with respect to the range, one can see, except this first point, that is the first nearest neighbor hopping T1, except the first point, all the hopping amplitudes can be fitted to a straight line to a log-log graph. So as it is a log-log, we can see that this Tn is having a kind of power law behavior, power law dependency on range n. And that power law exponent one can generate from the fitting. And we did that fitting of this straight line, and we got the Q here for different alpha value. So our model can be treated as a power law model, except this first nearest neighbor term. So we map this our Levi-Quasicrystal model to a power law hopping model, where we separated the first nearest neighbor term, and the rest of the terms can be calculated using that power law term n by 2 whole to the power q, where those q values we got from the fitting, and from the fitting we can see that q is almost equals to alpha plus 1, and also analytically we showed that it will be alpha plus 1 for a large n limit. So here we calculated how far or how close these our two Hamiltonians are. For that, we have calculated the trace distance between these two Hamiltonian, which represents the difference between the matrix elements of these two matrices, and which is given by this equation. And if we plot this trace distance with respect to alpha value, one can see this is of the order of 10 to the power minus 2 to 10 to the power minus 3. That is very much small. So from this trace distance, one can infer that these two models are almost same. But we also calculated the delta n, which represent the difference of the hopping amplitude coming from Levi-Quasicrystal model and the effective power law model. We mapped the model, and if we calculated this delta n relative difference, if we calculate, one can see for small n value, this relative difference is almost 30%. So these two models are not actually identical, but there is some equivalence between this Levi-Quasicrystal model and our effective model. So now for that, as these two models are not same, we go ahead and we plotted the energy spectrum of these two models, and we got very similar results. Here this blue region is delocalized and this pink region is localized, and this delocalized and localized region are separated by mobility edge, but this mobility edge region is having some unique features. So if we plot the fraction of states here with respect to the disorder. So if we notice only below this yellow dotted line, all the states are delocalized. But in between, if we see this yellow and green region, one can calculate that beta to the power 1 fraction of states will be delocalized here, but 1 minus beta fraction of states will be localized. So we can say this phase as P1 phase. Now, if we see in between this green and red region, green and red dotted line in between this region, one can notice that beta square fraction of states are blue, so that these blue states are delocalized, and 1 minus beta square states are pink, and these states are localized. So as beta square fraction of states are delocalized, we can say this phase as P2 phase. Like this, one can go ahead, and if beta s fraction of states are delocalized, we are naming this as PS phase. So this is the schematic summary of our work. This blue region is a delocalized states, and this pink region is a localized states, and this yellow, green, red, orange, blue, these regions are the PS phases regions, which is having the mobility edge. And for different alpha value, we plotted this phase diagram. And when we are approaching at alpha equals to 2, at alpha equals to 2, we will be getting back our normal Schrodinger equation. And if we discretize that normal Schrodinger equation, we will be getting the Aubry-Andr model. And Aubry-Andr model is not having any mobility edge. So one can see here the mobility edge region are shrinking here to 1 point. Only one can see a delocalization to localization transition. And our discretization procedure is not having this alpha equals to 1 point. There is some problem at this alpha equals to 1 point with that discretization procedure. So we separately calculated this alpha equals to 1 point, and we saw that there is a only delocalization to localization transition. There is no mobility edge region. So conclusion is there exists a parameter region for our model where all the states are either localized or delocalized. In between, there are those mobility edge regions are there, and those mobility edge regions also can be separated into different PS phases based on how much fraction of states are delocalized or localized. So we we established a connection between this space-fractional quantum mechanics and those unique kind of mobility edge phases, which is a feature of power law model. So as this Levy quasicrystal, now there are many proposals of experimental verification of space fractional quantum mechanics. So our Levy quasicrystal can be also experimentally verified, and as it is mapped to our power law model, so the theoretical prediction of the power law Aubry-Andr model also can be experimentally verified. So future plan is, so we can add in electron-electron interaction in our system, and we can see how the nature of the system is changing, and we can add a different kind of potential. Here we used a special kind of incommensurate potential, but if we change the potential, different kind of correlated potential if we use, and we can study the system with that kind of potential. Yes, thank you.
So thanks, Pallavi. It was very beautiful talk. So now our session is open for quick question. Participant can ask question to Pallavi, or you can write the question on chat box as well.
Thank you for your talk. I have two questions. So one is, why do you need localized states?
If the states are localized, then we will not be getting any transportation property from the system. So the material can be behave as a insulator. So getting that property of a material, we get the localized. We want the localization.
So what I understood, you are localizing eigenvalues, right? And doing that, you are concentrating the energy of the system to the localized region, right? Maybe I misunderstood. So
no, the wave functions are localizing here to a particular site.
Mm-hmm.
And this kind of insulators are different from the normal insulator. In the Anderson case, the diffusion is getting 0. So this is a different kind of insulator. In normal insulator, the carrier densities are 0. But in the Anderson insulator, as the diffusion is 0 and we are not getting any transportation, so it is good to study those systems.
Okay, thank you. One clarification. In one of your slides, you define disorder parameter W.
Yes.
I think in the starting. So how you identify value of W?
That we can take this
Yes,
W.
here.
Yes,
Yes.
yes. So in 1D and 2D for Anderson localization case, if we give this small, very small W also, one can see this localization. But for 3D, we have to give a high value of W. So there is a critical WC for that case. One can calculate the WC above which that localization will happen for 3D. But for 1D and 2D, if we choose a small W also, then also the state will be localized.
Mm-hmm. Thank you.
Okay.
Is there any other question? So if it is not, then we will move to our next talk. So thanks again, Pallavi.
Yeah,
And
thank you.
we are hoping to have you next year as well.
Yeah, thank you. Yeah.
Thank you.